This is a brief tutorial on multiphase systems for engineers. So we're going to cover, for example, the transition from liquid to vapor. And if we just start with this pressure versus temperature plot. Now this is for water, and this is a pressure here on the side. So you can see, logarithmic scale. So very, very low pressure. That is 1 atmosphere, so that's what we're used to running at, okay, at sea level. And if we start at very low pressure, okay, and 20 degrees Celsius, and then increase the pressure, okay, then we're going to have a liquid. Okay, and then as we increase the temperature, then we reach a certain point, 100 degrees in this case for 1 atmosphere, where it's going to transition back from liquid to vapor. Okay, and that's where it's going to boil. Okay, and then finally we're going to superheat our vapor. And so what we want to find is where the condensing to boiling line is, where the freezing to melting, or the freezing to sublimation is. Okay, so there is the condensing boiling line. So if we go across that phase, we go from a vapor to a liquid, or liquid to a vapor. Now this is the solid to liquid. Okay, so this is the freezing melting line, and then we also have a freezing sublimation. So at very low pressures for water, we can go directly from a vapor to a solid, or a solid to a vapor. Okay, this is just a pressure versus temperature diagram. One thing to note as well, you do have a supercritical fluid as well in this region. Okay, and we call this a gas when we are above the critical temperature, and the fluid behaves like a gas. Okay, so here is a pressure versus temperature diagram. Now this is for carbon dioxide, and this is 1 atmosphere. This is what we're used to, is where we take dry ice. Okay, the solid is like dry ice, and as we increase the temperature, okay, let's say we put it in outside, and we see it emits some vapor. Then at that point, negative 78.5 is where that's going to transition from a solid directly to a vapor. The dry ice does not become a liquid first and then a vapor. If we increased the pressure, okay, this is like 9.9, then we would go from a solid to a liquid, and then a liquid to a vapor as we increase the temperature. Okay, so we would have liquid CO2. Okay, so here is, we also have talked about a pressure versus volume. I just showed some pressure versus temperature. Okay, these are the pressure versus temperature, but this is pressure versus reduced volume. Now remember that reduced volume is equal to volume divided by the number of moles. Okay, so we have in this region we have our supercritical fluid. Okay, and then we have liquid on this side, and then vapor on this side, and then this is our two-phase region. Okay, so as we increase the pressure, for example, okay, we're going to start increasing here, and then it's going to transition from a vapor to a liquid, and then it's going to start compressing the liquid. Now you'll notice that this is a very steep, there, because the compressibility of liquid isn't very high. You can put a lot of pressure on it and the volume doesn't change very much, versus a gas is very compressible, and so the slope is less. Okay, and so this is a pressure versus reduced volume plot, and it shows a two-phase region. Okay, so just a couple definitions now for these two phases that we want to cover. Boiling point is going to be the temperature at which liquid changes to vapor. Okay, most people are familiar with that, but one thing that a lot of people don't know is it's a function of pressure. So as the pressure increases or decreases, that temperature at which the liquid changes to vapor, that's going to change. A normal boiling point, we define that as the boiling point at 1 atmosphere. Okay, so normal boiling point, 1 atmosphere. Okay, and then a freezing point, it's the temperature at which a liquid changes to a solid. And one thing that a lot of people don't know again is that this is also a function of pressure. Okay, not that strong a function of pressure, but it is a function of pressure. Okay, so sublimation point. Okay, again, that's just going from vapor or solid to vapor. Okay, vapor pressure then is let's just ask some questions about this. Why does a wet sidewalk become dry on a cold day if water boils at 200 degrees Fahrenheit, 212 degrees Fahrenheit? So why does it become dry? And what happens is you have vapor that is molecules, okay, at a vapor pressure. It's not going to boil, but it's going to be a fraction of, so when it boils then it's going to be equal to 760 millimeters of mercury as a vapor pressure. But if it's less than that, you're still going to have, let's say, 50 millimeters of mercury vapor pressure. So that vapor is still coming off, but it's just not boiling the liquid. Okay. Okay, and why does a 2-liter bottle of Sprite stay fizzy until you open it for the first time? Okay, so the gas is dissolved, the CO2 gas is dissolved, and you have a higher pressure. But as soon as you release the pressure, okay, then that it has a certain vapor pressure. It's going to start giving off the CO2 from the solution. Okay, and so why is humid air so uncomfortable in the summer? And part of the reason, let's say you have your hand here. Okay, I didn't do a very good job at that. Okay, so you're sweating, you have water vapor there, and if it's 100% humidity, then anything that is going to come off is also going to condense, and so you don't get the cooling effect of the water vapor. Okay, and why do swamp coolers work in the desert but not in the swamp? Probably for the same reason as this. Okay, and why does a wet finger dry faster when I blow on it? Okay, in this case, it's talking about the velocity. So I'm going to draw a finger here. Okay, and let's say it's this finger is wet, has some water on it, and then you blow on it. Okay, then what's happening is those water vapor molecules that are here are evaporating and condensing. Okay, but if you blow those water molecules away, then it's not going to condense back as much onto the finger, and so then it's going to feel cool. Okay, as more water evaporates and doesn't condense, and so that's also due to vapor pressure. So there's just some water molecules here that have vaporized even though we're below the boiling temperature. Okay, what happens to steam plume from a power plant? Okay, you might have seen, like, from a nuclear plant, a big steam cloud coming, and this is a white vapor. Actually it's a gas droplets. Okay, water vapor itself is clear, but what happens is same thing here. It's little droplets. If I zoom in on this, there's a little droplet and there's vapor. Okay, and that eventually all transitions to vapor, and you have no more droplets. Okay, and how do raindrops evaporate before hitting the ground sometimes? Okay, same thing, like these little droplets. Okay, so what is vapor pressure? Okay, we're going to use the PI star for vapor pressure. Okay, so it's a measure of the volatility of a species, how much propensity there is for it to transition, how easy it can transition to a vapor from a liquid. Okay, so for a pure component, the pressure of the vapor above the liquid at equilibrium. Okay, so if you just have a container just with one component in it, it's going to be the pressure of that vapor at when it equilibrates. Okay, so let's just redefine boiling point. Many of you have not thought about boiling this way, but it's just the temperature when the saturated okay, when the vapor pressure equals the total pressure. Okay, that's when you're going to start seeing bubbles, and that's when it's going to start boiling. Okay, so that's the boiling point of okay, that's going to be the boiling point of a pure substance. Okay, so let's just go over some compounds with high vapor pressures. Okay, they're going to evaporate quickly, and you can probably think of some of those like, ethyl alcohol, methyl alcohol. You've got some others that, gasoline, and you have some light components in that are going to very easily vaporize. Okay, you don't have to put low temperatures. They're going to be able to vaporize. Okay, and then what are some compounds with low vapor pressure, so they evaporate slowly, like motor oil, for example, or mercury. So there's others that have these lower vapor pressures, so they're not going to vaporize as easily, and they require a higher temperature to boil. Okay, so molecular level, let's just talk about what's happening on the molecular level. As the temperature increases, the molecules are going to start being more excited. They're going to have more energy. And some molecules exit the liquid phase, and this is happening all the time, and some molecules condense. Okay, so they're going to come out, going to be a gas, but then some of them are going to condense back into the liquid phase. Okay, so equilibrium is steady state condition where the same number of molecules condense and vaporize. Okay, and that's why when you blow on something, you're removing those, and then fewer are going to condense back. Okay, and that's why you feel, your finger gets colder when you blow on it, for example, a wet finger. Okay, so properties of vapor pressure. So this vapor pressure is a function of temperature. If you raise the temperature, more of the substance wants to be a vapor. Okay, so related to the volatility or tendency to evaporate at a given temperature. Okay, but this important thing is that this is going to be different for every species, and it's related to molecular weight. Okay, although we don't predict it based on molecular weight, and it's also related to chemical structure. Aromatic, for paraffins and others. Okay, so let's just look at the relationship to the heat of vaporization. So how much energy per mole is going to be required to vaporize a this compound. Okay, and this is a correlation from thermodynamics. Okay, so the change in vapor pressure with respect to temperature is going to be the heat of vaporization divided by temperature, and then multiplied by the difference in specific volumes between the gas and the liquid. Okay, so one of the things that we can do is just say that this is approximately 0 in comparison with the specific volume for gas. Okay, so the volume per moles is going to be much smaller for liquid. We'll just say that's approximately equal to 0. And then let's just rearrange this equation. Okay, and that's going to equal delta H of vaporization over temperature, and the specific volume of gas. Okay, so let's go ahead and use our ideal gas law. Okay, let me get rid of this N here. If we have a specific volume, it's just P times V hat equals RT. Okay, and then I'm going to solve for V hat. Okay, and then I'll plug that in right there for the gas. And what that's going to give me then is delta H of vaporization divided by, okay, and then that's going to be RT squared, and then I'm going to bring the P over to this side. Okay, and then I'm going to keep a dt here. And then if I just integrate both sides, then that gives me natural log of P star equals negative delta H of vaporization over RT squared plus a constant. And so this is just a constant of integration, and this is called the Clausius-Clapeyron equation. Okay. Okay, so we just derived the Clausius-Clapeyron equation, and we're going to use that to get an estimate for our vapor pressure from our heat of vaporization. Okay, so here's a vapor pressure chart, and so which compounds have the highest vapor pressure? This is going to be the vapor pressure here, and this is the temperature. Okay, so if I just look at let's say 212, okay, degrees Fahrenheit, and if I go up, then I can see that the vapor pressure is going to increase for these are going to be compounds that have very high vapor pressure, for example, and then as I go this way, they're going to be lower vapor pressures. Okay, so more difficult to vaporize. Okay, it vaporizes at higher temperatures. Okay, and here's water, for example, with some other compounds on there as well. Okay, so one way that we can predict vapor pressure is to use the Antoine equation. Okay, there's some different empirical correlations to come up with vapor pressure. Either we can use a chart, okay, we can just look it up on a chart, or we can use an equation. Now, you might want to use an equation, like let's say you have it in a mathematical optimization problem, or you're trying to you don't want to iteratively look up things from a chart. You can use an equation instead, and for every compound you're going to have a different value of A, B, and C, and that will give you the vapor pressure. Don't forget that's a log 10 right there. Okay, so this is just an empirical correlation Antoine equation. For different species, they fit it to this correlation, and it does a fairly decent job. Okay, there's also some so there's also, for example, the DIPPR Database. They use 5 constants instead, A through E. Okay, and then you can just go to this website, or you can go to hbll.byu.edu and go to databases. Okay, and then select the DIPPR database. Now you have to be on campus to be able to access this, but you'll have access to all of the compounds that are on the DIPPR database. Okay, so let's just look at, for example, table B3 in the textbook, and for ice, we'll have it from in that range, and then it's going to be water in that range. Ice and water will both have vapor pressures. Okay, and we can look those up. So let's just do this example then. What's going to be the difference in vapor pressure for this one versus this one? Okay, if we have less liquid here, what will the pressure be? Pressure 2 versus pressure 1. Okay, and the answer is they're actually going to be the same. It doesn't depend on the amount of liquid, it just depends on the temperature. But let's say we flip this this way. Okay, so we have liquid and then vapor. Okay, and more surface area. Is that going to change the pressure? And the answer is no. It might come to equilibrium faster because there's more surface area, but at equilibrium there's still going to be the same pressure. Okay, so they're going to be equal to the vapor pressure for a single species. Okay, well, what about moles in the liquid versus vapor? How would we calculate that? Okay, so how many moles? So here you have more moles. Here you have more moles in the liquid and less moles in the liquid, and here you're going to have more moles in, relatively to this one, more moles in the vapor. Okay, so how would you calculate that? For the vapor, you can do that just from the ideal gas law, okay, as long as you're at low enough pressures. And then for the liquid, you can just use the density and divide by and the volume and divide by the molecular weight for that liquid. Okay, so that can give you the number of moles of liquid and the number of moles of vapor. Okay, now you're going to see that this is going to be much, much less, okay, per volume than the liquid. Okay, so the liquid is going to be much more dense in terms of molar, the volume, or sorry, moles per volume. Okay, so let's go on to Raoult's law. Okay, so this just says that if you have, okay, so this is a relationship between yi, now that is the vapor mole fraction, okay, and then xi is going to be the liquid mole fraction. So before we used to define x as being, x was the mass fraction, but in this case, when you're talking about liquid and vapor, x is going to be the liquid mole fraction and y is going to be the vapor mole fraction. Okay, so it's related, the okay, so this is going to be the partial pressure, Pi, and that's going to be equal to, the mole fraction in the vapor times the total pressure. That's Dalton's law. Okay, and then when all those add up to the total pressure, but then this is the Raoult's law here, this correlation, where you also say that the liquid mole fraction times the vapor pressure, the pure component vapor pressure, for that is going to be equal to this partial pressure, okay, for that species. Okay, and so we want you to definitely memorize Raoult's law. Okay, this is a really, really important correlation. Okay, so special case is one species with both liquid and vapor present. Then you know that the total pressure is going to be equal to the saturated vapor pressure. Okay, because xi is equal to 1 and yi is equal to 1. Okay, so there's no other species. And if you have one species in the liquid and two or more species in the gas phase, then you know that the partial pressure is going to be equal to this, the saturated vapor pressure. Okay, and because xi is 1, but yi is not equal to 1. Okay, so let's look at our Gibbs Phase Rule. Okay, so this is the number of degrees of freedom. It helps us determine whether we need to specify temperature or pressure, or temperature and pressure, for example. Okay, so the degrees of freedom for multi-component systems is going to be equal to 2 plus the number of components, okay, minus the number of phases. Okay, and I sometimes just write it, 2 plus c minus p. Okay, but we use pi in this example. Okay, so let's just go through a couple examples with this. Single species, 2 phases. So you add the 2, and you have a single species, so 1 component, and then minus 2 phases. So that means you have 1 degree of freedom. So that means you can specify either temperature or pressure, but not both. Okay, so let's say we have 2 species and 2 phases. That's 2 plus the number of components is 2 minus the number of phases, which is 2. So that gives us 2 degrees of freedom. So we'll need to specify both temperature and pressure. Okay, so let's go through one example here. We have heptane in liquid, and then we have air and heptane in our gas. So we're just going to assume that the mole fraction of dissolved gas is very, very low, although there is going to be some in this. Okay, so let's just look at the Gibbs Phase Rule. So we have degrees of freedom. We take our 2 plus the number of species minus the number of phases, and that's going to give us 2 degrees of freedom. So we need to specify temperature and pressure. Okay, so let's go ahead and just specify those. We'll just go ahead and come up with 1 atmosphere and 25 degrees Celsius. We just made up those pressures and temperatures for this calculation. Okay, so now we want to calculate the mole fraction of heptane in the gas phase. So what we'll do is we'll first of all go ahead and calculate our vapor pressure at 25 degrees for the heptane. Okay, and then we'll use Raoult's law, and this is going to be equal to 1. So our Y heptane is going to be just equal to the vapor pressure of heptane divided by the total pressure. Okay, so let's just look up the Antoine coefficients to calculate this vapor pressure first. And so we just looked up the A, B, and C values and calculated it, and that's going to be 45.68 millimeters of mercury. 760 is 1 atmosphere for millimeters of mercury, so very low vapor pressure. And then if we do the calculation, now 46 divided by 760, and then that gives us our mole fraction in the vapor. Okay, so that is the end of this on multi-phase. We just briefly talked about some PT diagrams, and then also some PV diagrams. Okay, and then went over some definitions. What is vapor pressure, and then talked about what's happening at the molecular level, and then went over some correlations to be able to calculate vapor pressure. And also we introduced Raoult's law today. And then the other thing we introduced is also the Gibbs Phase Rule, and then went over one example. Okay, so let me go back and I'll just go ahead and stop this video. So go ahead and check back. We have more videos on chemical engineering fundamentals.